Hello everyone, I'm CY. Today I'd like to introduce IPv6 network slicing technology. First, let's look at the drivers behind network slicing. 5G defines three types of typical services. eMBB services are an enhanced to traditional mobile broadband and require ultra-large bandwidth and low latency. URLLC services require ultra-low latency and ultra-high reliability. MMTC services cater for Internet of Things and require a network that provides massive connections. Evidently, these three types of services have quite distinct requirements on the network, so that they can be carried on one network. 5G introduced network slicing. End-to-end network slicing consists of three parts: resource access network, mobile core network, as well as the transport network between them. The transport network is mainly used to provide on-demand connections between the resource access network and the core network, along with guaranteeing services (SLAs). This means the transport network slicing is an essential part of end-to-end network slicing. With regard to transport network slicing, its service requirement model can be divided into three layers. The bottom layer provides services isolation. At this layer, different types of services or users on the network are isolated without affecting each other. This is something we traditionally use VPN technologies for. But beyond this, network slicing must also be able to provide resource isolation. This ensures that services with strict SLA requirements are assigned exclusive resources and are not affected by other services on the same network. The top layer provides O&M isolation. This capability is required by some vertical industry users who need to have independent management and O&M of network slices. They want to use network slices in the same way as they use in traditional private networks. From preceding three layers requirement model, we can see that the traditional VPN technologies are unable to meet the requirements of network slicing. Instead, they need to be extended and enhanced to provide resource isolation and O&M isolation. This is where enhanced VPN comes in. Enhanced VPN is also referred to as the IP network slicing solution. Now, let's look at the overall architecture of IPv6 network slicing. As shown in this figure, IPv6 network slicing consists of three layers. At the bottom is the network slicing infrastructure layer, which provides on-demand resource partition and isolation capabilities for network slicing. At this layer, we need to partition nodes resource and the link resource required by network slices so that these slices are isolated in resources. The resource partition technology can be FlexE or another one. The layer in the middle is referred to as the network slice instance layer. At this layer, customized network slices virtual topologies are created, and the logical overlay network connections are mapped to and combined with underlay network resources. This layer is further divided into data plane and control plane. The data plane mainly provides the network slices identifiers and forwards network packets based on network slice constraints. In contrast, the control plane mainly distributes network slices attributes such as topology resources to the involved controller and the network nodes, so they can perform constraint-based path computation. At this layer, we will consider using IPv6 enhanced technologies to instantiate network slices. The management and control system at the top layer is mainly used to manage the lifecycle of network slices, including creating, monitoring, adjusting, and deleting slices. By using the Young model of network slicing, the layer enables interconnections between standardized interfaces and users. Let's now take a closer look at how IPv6 enhanced technologies are used to instantiate network slices and what benefits of doing so. As a fundamental network protocol in the 5G and cloud era, The IPv6 provides vast numbers of addresses needed for massive connections on 5G networks. IPv6 enhanced technologies further unleash the potential of IPv6. For example, SRv6 enables network programming, while various IPv6 intention headers enable packets to carry richer information. Another key benefit of IPv6 is that it can seamlessly unify the overlay and underlay networks. For network slicing, IPv6 Enhanced offers the following advantages. First, on the data plane, by taking advantages of flexible programmability of IPv6, IPv6 Enhanced enables data packet headers, which can be the SRH or another types of the IPv6 intention header, to carry the network-wide unique network slice identifiers, guiding the packet forwarding based on constraints of network slices. The IPv6-based data plane is seamlessly compatible with traditional IPv6 networks, thereby facilitating incremental network evolution. Second, the control plane. IPv6 enhanced the reuse and extend IGP and BGP protocols to distribute network slice information to other network nodes and the controller. In doing so, it implements path computation based on network slice constraint. To combine and to extend the existing technologies in the control plane, while making minimal changes to them, avoids significant investment of developing new protocols. Third, in terms of scalability, IPv6 Enhanced inherits characteristic of source routing in SRv6, eliminating the need for introducing state of each path into the network. This is vital for supporting a great number of network slices. Further to this, IPv6 network slicing on the basis of SRv6 is capable of reserving resources on a per network slice or per segment basis to allow different network slices to flexibly share or isolate resources. Now, let's take a look at how network slicing works in practice. I'm going to use smart grid services as an example. Such services require extremely high reliability. This means they must be strictly isolated from other services. But the requirements of power grid services are not the same, because they include both production services and management services, which have varying network SLA requirements. For example, differential protection services require ultra-high reliability and low latency. But inspection services, including intelligent robot inspection and jaw inspection, require a network to provide high bandwidth. The intelligent meter reading services, on the other hand, require a network to provide massive connections. For these different types of power grid services, we also need to provide corresponding isolation to ensure their SLAs. So, how can our IPv6 network slicing solution achieve this? At the network infrastructure layer, we need to create different flexi interfaces for different slices and services to ensure strict resource isolation. At the network slices instance layer, we need to use IPv6 enhanced technologies to distribute network slices identifiers to different slices in the data plane, so that slices services are mapped to corresponding flexi interfaces, thereby ensuring resource isolation between services. In the control plane, we use the extended IGP and BGP protocols to distribute the topology and the resource attributes of network slices to the controller and the network nodes. For services requiring strict SLA assurance, the controller performs strict SRTE path computation to meet their requirements. For other types of services, it is possible to use distributed path computation, based on network slices constraint to isolate slices services from others, while providing flexible on-demand connections. That's all for this video on IPv6 network slicing.